This is Jack Jackson. In this video we're going to look at the concept of limits. This is an introductory video and an informal introduction to this fundamental calculus concept. In fact, the limit is the fundamental concept in calculus. All calculus is really derived by just taking pre-calculus concepts and applying this limit concept to them. And this results in a powering up of the tools of pre-calculus so that we can obtain some calculus tools which enable us to solve much more complicated and realistic problems and applications. So then, what is a limit? Well, basically a limit, the basic idea of it, intuitive idea, is that we take a function, and by the way, remember a function is a bunch of input and output pairs. You have inputs and outputs, first coordinates, second coordinates. Okay, x's and y's, or x's and f of x's. So, for a limit, we take this intuitive idea of a function, inputs and outputs. We let the input variable x get closer and closer to a particular value, call it c, and we want to see then what the other value, the y value, the output value, what it gets closer and closer to, whether we call that output value y or f of x. We want to see what it gets closer and closer to. And if it has a limit, it'll get closer and closer to a specific value, L. So this is the basic idea of a limit as x approaches a constant. So we say a function f approaches the limit L as x approaches the constant c, if and only if when we let the input values of x get closer and closer to c without actually being c, then the output values of f of x get closer and closer to the limit L. And we use the notation, the limit as x approaches c of f of x equals L, like that. Okay, so let's look at this at an example. So let's take the function for our first example, f of x equals 3x, and we want to find the limit as x approaches 2 of f of x. So what are we asking about in terms of the graph? Well, in the graph and in the table, we want to look at f of x equals 3x and see if we let the x values get closer and closer to 2, what do the y values get closer and closer to? And so we can look at whatever portion of the graph or portion of the table we would like. And here's a portion of the graph. And you can see that if we take this and let's say we're taking this graph, what we're talking about here, the x is 2, and I think you can see the y's are getting closer to 6. So as x gets in closer and closer to 2, the y's come in closer and closer to 6. So if you just follow this along the graph, we can see that as we're coming in from the right side, we're coming this way, and we come in from the left side, it's approaching that same point, which is the point 2, 6 on the graph. So that limit here actually equals 6. It equals that y value that it's getting closer and closer to. How do we see this in a table? Well, we want to put in our table, what do we want to put in? Well, we want to put in x values that are close to 2. Not necessarily 2 itself, but things that are close to 2 and getting closer and closer. So we might start kind of close to 2. Here, let's start above 2 with 3 right here. Okay? And so we take 3 and we want to see what y is. Okay? And our formula is y equals 3x, so 3 times 3 is 9. Then we get a little closer, so come in a little closer this way. Get a little closer to 2. Let's closer to 2 than 3, but let's say still on the right side would be, say, 2.5. 3 times that is 7.5. Come in a little closer still. How about 2.1? 3 times that is 6.3. How about closer still? How about 2.01? 3 times that is 6.03. Okay, it looks like these guys here on the y's are coming down. They may be getting closer to maybe 6, looks like. Okay, let's look like on the x's on the left side. So we can start with 1. 1 times 3 is 3. Go a little closer to 2, 1.5. 1.5 times 3 is 4.5. So the x's are coming in closer and closer to 2 here. What do these y's get closer and closer to? Let's get even closer still to 2. How about 1.9? And then we could do 3 times that is 5.7. 1.99, 3 times that is 5.97. We could get even closer still, but if we get closer and closer and closer, we see that these y values here are getting closer and closer to 6 as we come in closer and closer to 2 with the x values coming from either side. So what we're doing is we're investigating those input-output pairs, okay, as we get closer and closer and closer, and we see to 2 without actually being 2, and that's what we looked at in both the table and the graph. And in both cases we could see that it appears that the limit is going to be 6. Now in this particular case, this is what we call a continuous function. Notice that the point 26, not only is it our limit value, it actually is a point actually on the graph. Okay? And so what that's going to mean for us is not only are we getting closer and closer to that point 26, but that point right there is actually a point on the graph, and it's getting closer and closer to that. So if we draw a little circle around that, we have one connected piece within that circle. That circle is called a neighborhood, and within that neighborhood it's all connected. This is what it looks like for what we call a continuous function. Okay, and what it takes for it to be a continuous function is for the function value to exist and the limit to exist, and those to be the same. So here we have f of 2 is 6, the limit as x approaches 2 is 6, those are the same thing. So that's what we say it's continuous at that point. We'll talk a little bit more about continuity in a later part of these notes in a later video. Now in this case, since it was continuous, we could have just found the limit by plugging in 2 in the formula and see that output is 6. Let's look at another example that's maybe a bit more interesting, because this one has a discontinuity where we want to look at. Now let's first look at this one here. For example 2. F of x equals x to the 0 power. Find the limit as x approaches 0 of f of x. Now before we go any further, let's review some real basic properties of exponents. X to the 0 power is 1 for any x that's not 0. 0 to the x is 0 for any positive x power. But 0 to the x is undefined if x is negative, because that's equivalent to dividing by 0. So remember, 2 to the negative 3 is the same as 1 over 2 to the third, or 1/8 for example. So 0 to the negative 2 would be 1 over 0 squared, 1 over 0, and dividing by 0 is undefined. More about dividing by 0 in just a minute. So what about 0 to the 0 power? If you look at the first rule right here, it looks like 0 to the 0 power, that rule would kind of indicate maybe it ought to be 1. But if you look at the second rule, it indicates that, well, maybe it ought to be 0. Well, because these rules don't line up and they don't match, we can't get a consistent single answer for what we're going to get here for 0 to 0. And because of this, we say that 0 to 0 is indeterminate. It's the word that we use for that. Okay, so indeterminate. And if it's indeterminate, that means it's undefined. We just simply leave it undefined. In other words, 0 to 0 does not even exist. Now, if you need a little bit more refresher on some of these properties of exponents and want to go through what all this stuff means with exponents from the very, very first principles, I direct you to some of my videos in my algebra videos. You can find this on Unit 4. You can see the first couple of videos there under exponents, radicals, and power functions. If you can look at that playlist, you can see a little bit more about exponents. Might be useful to review that. Now let's consider another function. g of x equals x over x. Now let's think about this a minute. First of all, what does it mean to divide? Well, division is just answer to a multiplication problem. So when you say 6 divided by 2, whether it's written as a fraction or this way, it's 3 because 3 is the only solution to 2 times x equals 6. So when you're solving 6 divided by 2, call that x, then this x has to be able to solve this equation. 2 times x equals 6. So solving a division is solving a missing factor multiplication problem. Either 2 times x equals 6 or x times 2 equals 6. 2 times x equals 6 means you're taking the 6, dividing it into 2 groups, and you want to see how many is in each group. Or if you're thinking of it as x times 2 equals 6, it says you have 2 in each group and you want to find how many groups. Either way, the answer, of course, is 3. Now, similarly, 0 divided by 2, whether you write it this way or this way, is 0 because this last 0 is the only solution to the equation 2 times x equals 0. Now, however, consider what happens if we try to divide a non-zero number by 0, for example, like 2 divided by 0. Well, let's call that x. Whatever x this is has to be a solution of that 0 times that x has to be equal to 2. But 0 times x is 0 no matter what x is, and 0 is not equal to 2, so this equation has no solution. So, in a sense, nothing works here. Nothing solves the related multiplication problem, so dividing a non-zero number by 0 is undefined. Now let's consider what happens when we try to divide 0 by 0. If you say 0 divided by 0 is x, it's got to be a solution to the second 0 times x has to equal the first 0. Well, what's the solution to that? Well, anything. 0 times anything is 0. Any real number works. So 0 divided by 0 has infinitely many potential values. So in other words, the 0 times x equals 0 has infinitely many solutions. So this is also an indeterminate form like 0 to the 0 power was. And so once again, it's undefined, kind of for the opposite reason that 2 divided by 0 is undefined. 2 divided by 0 is undefined because there's no solution to this related multiplication problem, missing factor problem. And 0 divided by 0 is undefined because there are infinitely many solutions to that. In fact, anything works. So in either way, though, division by 0 is undefined in either case. So g of 0 up here is undefined, but if you got any other value, any other number divided by itself is 1. So actually, the functions f and g are the same function. The function x to the 0, y equals x to the 0, or y equals x over x, are both equal to 1 when x is not 0 and undefined when x equals 0. So here's the same function written 3 different ways. We could write it as f of x equals x to 0, we could write it as f of x equals x over x, or we could write it f of x equals 1 when x is not 0 and undefined when x equals 0. Well, what does a graph look like? Or what does a table look like? Let's look at the table first. Now we're interested in what's happening when x is 0. Well, when x equals 0, nothing happens. It's undefined. It does not have an input of 0. 0 is not in the domain. Another way to say that is if you draw a vertical line there, which is x equals 0, that's the y-axis. The y-axis does not touch this graph. The graph does not touch the y-axis at all. It has no y-intercept. However, otherwise, every input is 1. So if we let x's get close to 0, but not 0, we're looking at x's like negative 1, negative 0.1, negative 0.01, negative 0.001, getting closer and closer to 0, but not being actually equal to 0. Or from the right side, 1, 0.1, 0.01, 0.001. So the x's are coming in here close to 0, and what are the y's? Well, this function, every y is 1, where it's defined, and so certainly the y values are getting closer and closer to 1. In fact, they are 1 every time. So they're certainly close to 1. They are 1. So that limit is actually 1. So here's an example where the function does not exist at 0 when x is 0, but the limit does exist. So this gives us something kind of new with calculus that we didn't have with pre-calculus. It gives us a way of looking at talking about a limit. Okay, so what does the graph look like? Well, here it is, down here, the green. The graph actually, all the points, all the y values are 1, so that's a horizontal line, except this one has a hole in the graph, and you can see that right there. Do you see how that kind of goes around and leaves a hole in the graph? Okay, right there. Okay, so that hole in the graph is something kind of new compared to the last example. So that's a discontinuity. Okay, there is a break in the graph. If we draw a little neighborhood around that point, it is not one connected piece. There's a break right at there. Okay, so that point 0, 1 is actually what we call a hole in the graph. It was just probably more descriptive. It's also sometimes called a removable discontinuity. It's called a removable discontinuity because if we all we have to do is just add one more point or change one point from undefined to actually the point 0, 1, and then we would have it's continuous there. We can plug the hole. So I kind of like hole in the graph better because it's a more descriptive term of what's happening with the graph, but a technical term would be removable discontinuity. Now, we can also talk about some other things, other kinds of limits. Okay, so that was a full limit as x approaches a point, a specific value. Now, in this case, we're going to look at some one-sided limits. We can say the limit as x approaches c, and see that little plus there? That means we're approaching from the right side. So we say the limit as x approaches c from the right side of f of x equals L. That's a right-sided limit. So we let x approach c, so it's getting closer and closer to that value of c. Okay? But x always has to be a positive, not necessarily a positive number, but to just a little bit to the right of c. Of course, if c is a negative number, that will be still a negative number, but it will be on the right side of c. So the plus doesn't necessarily mean a positive number, it just means from the right side. Okay? Similarly, what about a left-sided limit? It looks like the limit as x approaches c from the left of f of x is L. So what that indicates that x approaches this c value again, getting closer and closer to c, but x has to be below, that is, to the left of c. So again, this superscript negative there on the right side doesn't mean a negative number, it means close to c. If c is a positive number, then these x's we're looking at are positive numbers, but close to c, but always below c from the left side. So the only way you can get a full limit to exist if both of these left and right limits exist and they are the same L value, the same limit. One way a limit would fail to exist is if you had left and right limits, but the two limits are not the same. In that case, we say the full limit just does not exist. It is undefined. Now we have a couple other things we can do. We can let a limit approach instead of approaching a constant, we can let the x approach infinity or minus infinity. So we could say the limit as x approaches infinity of f of x is L. That means we're going way out to the right with x. Further and further and further and further out to the right of the graph. So x is getting larger and larger and larger, increasing without bound. And the further out we go, the closer the y gets to the value L. Similarly, we can go far to the left. That's the limit as x approaches negative infinity. And the x values are decreasing without bound, going farther and farther and farther to the left on the graph. And we see that the y's are getting closer and closer and closer to some value L. So let's look at this in a graphical example or two. So here we have some limits from a graph. Now suppose that f is a function defined by this particular graph. So this is one function. The formula might be kind of complicated because it's made up of lots of pieces. It is actually a function. If you look at it, every input gives you only one output. That makes it a function. In other words, it passes the vertical line test. So for example, when x is 10, the point is actually here, but there's not one down here or anywhere else on that vertical line. And you can do the similar kind of thing anywhere along here. Now, what we want to do is we want to talk about some of these limits. So, for example, let's in function values. So the first thing is, let's look at f of 8. Okay? F of 8 is the y value when x is 8, and you can see right there that it is 4. Okay? So that's saying that the point 8, 4 is on there. What about the limit as x approaches 8? Well, as we come in here, this way and this way, we're getting closer and closer to the same y value, which again is 4. So it's actually continuous at that point. What about f of 5? Well, f of 5, I don't see a point there. Oh, here it is, up here, way up here. So f of 5 is actually 8. What's the limit as x approaches 5? Well, as you get closer and closer to 5, but not actually at 5, we can see that the y values are getting closer and closer to that y value right there, which is 1. So there we have a limit, and we have a function value, but they are not the same. So that's a discontinuity. That's also a hole in the graph, or removable discontinuity, because we could redefine the function by erasing this point up here, which we would call an isolated point, and moving it down here to plug up the hole, and by moving only one point, we could make it continuous there. Okay, let's look at some more examples. F of 7. Okay, let's find, whoa, come back here. F of 7, here's 7, undefined there. Let's see, is it defined anywhere? Okay, I don't see a point anywhere. So we would say that just does not exist. Does not exist. It's undefined. What about the limit as x approaches 7? That does exist. That's a hole in the graph. We have a hole in the graph there. So as we approach that, we get a value. What is that y value? It is 3. So that limit is 3. So again, a hole in the graph. F of negative 2 next. Alright, right there's the point that has a y value of 1. So that's our function value. What's the limit as x approaches this? Well, it actually does not exist. Why? Because the left and right limits are not the same. Let's look at the left and right limits. So this, let's see, where am I? Back up here. If we come from the right side, it does have a limit, and it is 1. If we come from the left side, look what happens here. It's going down this way forever, decreasing without bounds. So you might see like a little arrow there on the end of that. Okay, well, since that goes down forever, we would say the limit does not exist, but we can be more specific. We can say that y value is approaching negative infinity, which means it's decreasing without bound. As we get x get closer and closer to negative 2, but from the left side, the y's go further and further and further and further down, way down into the negatives. Okay, and so we would say that's negative infinity. Notice this is not saying that that one-sided limit exists. It's telling you how and why it does not exist. Continuing on, f of 10, that's actually got the point right there, so that's 6. Okay, let me go down here where I've got them already worked out. F of 10 was 6. And let's see, look at this. We have a left limit of 6. We have a right limit of 4. Okay, so the point 10, 4 is an open dot boundary point. The point 10, 6 is actually filled in, so that's a closed dot boundary point. Okay, so limit from the left is 6 and from the right is 4, but since they do not match, that means the full limit does not exist. Finally, we can talk about limits as we go to infinity and negative infinity. As we go out to infinity, we're talking about going out here. And it looks like, if you look at this, that we're getting closer and closer to this line right here. that's the line y equals 2. And in this case, it's getting closer and closer without actually touching it. That's called a horizontal asymptote. Okay? And that limit is 2. On the other hand, if we go out to the left forever, it actually goes down forever. So we say that's approaching negative infinity. Finally, remember that the function, the limit of the function as x approaches c has nothing to do with what, if anything, actually happens on or at the function when x actually equals the c value. Okay? So now let's go back here and let's do a couple more examples. Okay? This time what we're going to do is I'm going to try to have you do these yourself. So here's the graph. What I'm going to do here is scroll down, tell you the places I would like you to find the limits, then come back and then I'm going to come back to the graph. I'm going to show you the limits. You pause and write it down. We'll come back to the graph. I'll pause. You pause, work out the answers, and then press play again, and then we'll resume. Okay? So here are the limits that we want to try to compute in this case, and function values. F of negative 6, excuse me. The limit as x approaches negative 6. F of negative 5, the limit as x approaches negative 5. The left and right limits as x approaches negative 5. F of 0, the limit as x approaches 0. F of 5, and the limit as x approaches 5. Full limit, and then from the left and right. F of 12, the limit as x approaches 12, and then the limit from the left and right. And then the limits as x goes to infinity and negative infinity. And then list all the discontinuities. So jot those down real fast, which ones we want to do. Okay, if you need to, press pause and jot those down. Okay, if you need to, write some more down. Here they are. Okay, now let me put it back on the graph. Since you know where we're looking, now work this out yourself. Press pause now. Come back when you're ready. Okay, if you worked out all these limits, we should be able to now go down here and answer this question. So let's see what we've got here. So first of all, we want to look at negative 6. Well, if you look, this does not touch the vertical line at x equals negative 6. This grid line does not touch the function at all. So f of negative 6 does not exist. That is one possible answer, and it's right in this case. But the limit as x approaches negative 6 does exist, and you can see that's a y value of 4. F of negative 5 is this point, indicates this point here at negative 5, negative 3, so the answer is negative 3 for f of negative 5. But the limit does not exist. Actually, let's see, did it ask us some more things? Yeah, the limit as x approaches negative 5 from the right side approaches right here at 0, but that's not an actual point. Probably it should have actually looked a little bit more like this, showing that open boundary point there and there. Okay. But then the limit as x approaches negative 5 from the right side is infinity. It's going to infinity here. Again, that's not saying that the limit exists. It's showing you why and how it does not exist. Okay, f of 0, this claims it's 5. That's this point right there, and that's a point that's actually on the graph. And so that means it's f of 0 is 5, but the limit is also that. So that's the function's continuous there. How about f of 5? F of 5 is actually down here, which is at 2, negative 2. Okay, but the limit does not exist. Why? Because the limit from the left is 0 and the limit from the right is negative 5. Is that right? Yeah, if we come in from the left side, the y's are approaching 0. Coming from the right side, the y's are approaching negative 5. And I bet next we want to look at 12. Yep, f of 12, the y value is right here. The point is right there, so the y value is 2. Up here is 3, so the limit from the right is 3, the limit from the left is 2, so the full limit does not exist. Okay, and finally, let's look at the limits as we go to infinity and minus infinity. It looks like as we go to infinity, it's approaching 0, and negative infinity, it's approaching 3. So there we had asymptotes. Now, where do we have discontinuities? Discontinuities are anywhere we have any kind of a break. One occurs right here when we want just the x values, -6. One occurs here at -5, right here. Next one's here at 5. The next one's here at 12. And everywhere else, it's continuous. So anywhere else, if we draw a circle, we could make it one connected piece. But here, there's going to be a break somehow. Alright, let's do another example like this. Okay, so once again, I'm going to show you the graph briefly. Then we're going to look at the things where we want the limits. So again, jot these down. Okay, we want to find f of 10, and the limit as x approaches 10. Write that down. F of -4, and the limit as x approaches -4. Both full limit and both of the left and right limits. We want f of 0, and the limit as x approaches 0. We want f of -2, and the limit as x approaches -2, and the one-sided limits. Number 5, we want f of 5, the limit as x approaches 5, and the one-sided limits as x approaches 5. And then we want to go to infinity and minus infinity. So jot all those down. Remember, the last two are going to infinity and minus infinity. If you need to, stop here, press pause, and write all these down. When you're finished writing them down, then, like I said, press pause if you need to. Come back and we'll look at the graph. Press pause. Okay, now you should have finished writing them down. Now go back to here to the graph and see if you can determine those limits. Okay, work it out for yourself. You should be able to do this at this point in the lecture here. You should be able to do this on your own, and if you can, we'll check it out here in just a minute. So press pause now. Come back when you're ready. Alright, now you should have worked all this out. So let's go ahead and look at the answers here. Okay, f of 10. Here's 10. Looks like it's going right to that point right there, which is 5. 10, 5. So 5 is f of 10. And the limit as x goes to 10 is also 5. It's actually continuous right there. F of -4. 1, 2, 3, 4. F of -4 is right there, that point, which is 0. But the limit does not exist because the left and right limits, even though they do exist, are not the same. The limit from the left, -4 from the left side, which is what this means right here, is approaching this way, which is a y value of -6. Whereas if we're coming in this direction from the right, approaching -4, remember the -4 is the x value here, the y is approaching 0. F of 0 is undefined. No, that's wrong. There's a point there at -5. Let me fix that. Okay, give me just a second to correct that mistake. So it should be at -5. F of 0 is -5. There we go. We fixed that. But the limit as x approaches 0 is 0. So we have a hole in the graph right there at 0, 0, but we got an isolated point down here at 0, -5. Okay, let's try it -2. Okay, looking up and down the graph, it never actually touches that vertical line at x equals -2. So we say that it is undefined there. It does not exist. And the limit does not exist either. More specifically, if we come in from the left side, okay, coming in like this, it's going up forever, so we say that's going to infinity. And we come from the right side, and that's going to minus infinity. If you're approaching a specific constant, like -2 for x, and the limit, even from one side, is either infinity or negative infinity, at least from that side, we have what we call a vertical asymptote. That's asymptote. So this is a vertical one. That is x equals -2. This line right here, that grid line, is the asymptote. The graph is approaching it asymptotically. Now there's actually a point down here, so if this is a function, that's an open dot there. I think that may be our next one. Sure enough, f of 5 is actually given by that point, which is 5, 1, so the f of 5 is 1. The limit as x approaches 5 is approaching this point right here, which is 5, 5, so the limit is that 5 there. X is approaching 5, and y is approaching 5. And of course, left and right limits are both 5. Now what about x as approaches infinity? This is an interesting one. This thing is bouncing up and down forever, but less and less and less and less as we go out. And you see that it's getting closer and closer and closer to 5, even though it's still going above and below it. So it's not really an asymptote, but it's still approaching that limit, which is 5. But if we go to minus infinity, as you go out this way, what will happen to the y's? They're going down forever. So we would say that limit is minus infinity, which again is not actually a limit, but is just saying how and why it doesn't exist. In our next video, we'll look at some limits just you looking at a table rather than looking at a graph.